In this video, I will talk about maximum average power transfer theorem in case of AC circuit. I will show you the condition for which the circuit will receive maximum average power from the AC circuit, and I will show you the formula of that maximum average power that will be transferred to the load impedance ZL. During DC circuit analysis, we solved the problem of maximizing the power delivered by the resistive network to a load of RL. Representing the circuit by its Thevenin equivalent circuit, I showed you that a load resistance RL receives maximum power if the value of RL is exactly equal to the Thevenin resistance of the circuit, and the value of maximum power that will be absorbed by the RL should be equal to VTH square over 4RTH. This was applicable in case of DC circuit, and that theorem is known as maximum power transfer theorem for DC circuit. But in case of AC circuit, the theorem is maximum average power transfer theorem, because the load impedance will have both real and imaginary part, and we know that the reactive part does not absorb any power, rather it stores power, and that reactive power flows back and forth to the circuit, so that the over a full cycle the average power consumed by the reactive part is equal to 0. Therefore, this theorem is maximum average power transfer theorem. We will extend our analysis of maximum power transfer theorem in case of AC circuit, and that will be maximum average power transfer theorem. Maximum average power transfer theorem states that a load impedance ZL receives maximum power from an AC circuit if the value of load impedance ZL is the complex conjugate of the Thevenin impedance of the network, and the value of maximum average power delivered to the load impedance will be equal to magnitude of Thevenin voltage square over 8RTH. Here this RTH is the real part of the complex conjugate of the Thevenin impedance. Okay, now I will show you the derivation of these two conditions. I will show you that the circuit will deliver maximum power to the load impedance when ZL is equal to the complex conjugate of ZTH, and the maximum power will be VTH square over 8RTH. Let's say I have a linear circuit connected across these A and B terminals. Linear circuit, that means I can have several voltage sources, AC voltage sources, AC current sources, resistance, inductance, capacitors connected within these two terminals, and I have a load impedance ZL connected in parallel to these A and B terminals. This load is usually represented by an impedance, which may be an electric motor, an antenna, and so forth, which can consume AC power. From Thevenin theorem, we know that we can reduce the linear circuit to a Thevenin voltage source VTH in series with an impedance ZTH. So if I convert the linear circuit to a Thevenin equivalent circuit, I will get a circuit like this. So our circuit will look like this. Within this A and B terminals, I will have the load impedance connected here. Okay, let's say I am representing the Thevenin impedance of this linear circuit in rectangular form, ZTH equal to RTH plus JXTH. This RTH is the resistive part of the Thevenin impedance, XTH is the reactive part, and I am representing the load impedance in rectangular form, ZL equal to RL plus JXL. This XL is the reactive part of ZL, and RL is the resistive part of ZL. This total circuit will be a series circuit. So current will be same all over the circuit. Let's say the phasor current at load impedance is IL. So the total current IL in the circuit will be equal to VTH over ZTH plus ZL. Here VTH is the total voltage of the network, and ZTH plus ZL is the total impedance across these two terminals. Okay, now see, If I put the value of rectangular form of ZTH and ZL here, I will get VTH over RTH plus JXTH plus RL plus JXL. Now if I separate out the real and reactive parts, I will get RTH plus RL plus JXTH plus XL in the denominator. So this will be our phasor current in the circuit. Now see, the voltage across this A and B terminal is VL. If I use voltage divider rule, I can calculate VL. VL will be equal to ZL over ZL plus ZTH into VTH. So here VL will be equal to VTH into ZL over ZL plus ZTH. We use voltage divider rule here. Now see, if I put the rectangular form of ZL and ZTH here, we will get VTH into RL plus JXL over RTH plus RL plus JXTH plus XL. Now we will find out the magnitude of phasor current and phasor voltage at the load impedance ZL. See here, the magnitude of phasor current IL will be equal to VTH over root over RTH plus RL whole square plus XTH plus XL whole square, and the magnitude of phasor voltage across load impedance will be equal to, here we have real and imaginary parts, so we will take the VTH into root over RL square plus XL square over the magnitude of denominator will be root over RTH plus RL whole square plus XTH plus XL whole square. So magnitude of IL and magnitude of VL will be these two quantities. Okay, now see, ZL has both real and reactive parts. The reactive part does not consume any power, so the power in the reactive part over a full cycle will be equal to 0. So the power that will be absorbed by the load impedance will be equal to PL. PL will be equal to the IRMS square RL, as power will be absorbed by the resistance or resistive part of the load impedance. Here the relation between the phasor current and RMS value is equal to IL over root 2 whole square RL. So power delivered to the load PL will be equal to IRMS square over IRMS square into RL. If I put IRMS equal to IL over root 2, I will get IL square RL over 2. Now see, IL is equal to this VTH over root over RTH plus RL whole square plus XTH plus XL whole square. So if I put the square of IL, I will get PL equal to the power delivered to the load ZL equal to VTH square over RTH plus RL whole square plus XTH plus XL whole square into RL over 2. This will be an important equation for us. Let's say this is equation number 1. Now look at equation number 1. PL is equal to VTH square into RL over 2 RTH plus RL whole square plus XTH plus XL whole square. Here see, the power delivered to the load impedance ZL is a function of RL and XL. Our objective is to adjust the value of load impedance parameter RL and XL so that PL becomes maximum. From calculus we know that at maximum point the slope of a function is 0. Here PL is function of RL and XL. So if I want to calculate the maximum power, I have to take the partial derivative of PL with respect to RL and partial derivative of PL with respect to XL, and for maximum power both of them will be equal to 0. I have to satisfy these two conditions: partial derivative of PL with respect to RL is equal to 0 and partial derivative of PL with respect to XL equal to 0 for maximum power to be delivered to the load impedance ZL. Okay, so this is our equation number 1. At first I will take the partial derivative of this equation number 1 with respect to XL, and after that I will take the derivative with respect to RL. So if I take the partial derivative of equation 1 with respect to XL, I will get delta PL over delta XL, and for maximum power this will be equal to 0. Okay, so if I take that, see here VTH square into RL over 2 will be constant. So here I will get VTH square into RL over 2. Then I will take the derivative of RTH plus RL whole square plus XTH plus XL whole square minus 1 with respect to XL, which will give us equal to VTH square RL over 2 into minus 1 over RTH plus RL whole square plus XTH plus XL whole square into 2 XTH plus XL. Okay, and this will be equal to 0. If I write it clearly, I will get VTH square RL over 2 into minus 1 sorry, this will be whole square RTH plus RL whole square plus XTH plus XL whole square into 2 XTH plus XL equal to 0. Now see here, these are constants, this is minus 1. From here I can write XTH plus XL is equal to 0. Here this will be equal to 0. Okay, don't forget it. So for maximum power, the value of reactance will be equal to the minus of Thevenin reactance of the circuit. This is a condition. Let's say this will represent equation number 2. For maximum power, XL will be equal to minus XTH. Now I will take the partial derivative of PL with respect to RL. Here PL is equal to VTH square over 2 RL over RTH plus RL whole square plus XTH plus XL whole square, and this will be equal to 0 for maximum power. Okay, here VTH square over 2 will be constant, so if I take it in the right side, I will get RL equal to RTH plus RL whole square plus XTH plus XL whole square with exponential of minus 1. Okay, now see, I can use the formula of d dx of uv, where u dv dx plus v du dx. Okay, now see, if I use this formula, here I can write down this partial derivative as RL into DRL RTH plus RL whole square plus XTH plus XL whole square with exponents minus 1 plus RTH plus RL whole square plus XTH plus XL whole square minus 1 DRL of DRL. This will result 1. So here I can write down minus 2RL into 2RTH plus RL over RTH plus RL whole square plus XTH XL whole square over whole square plus 1 over RTH plus RL whole square plus XTH plus XL whole square. Now see, if I take the LCM of these two terms, I will get minus RL into 2 RTH plus RL plus RTH plus RL whole square plus XTH plus XL whole square. See, from equation number 2 we know that for maximum power XL has to be equal to minus XTH. So if I put XL equal to minus XTH, this term can be replaced with 0. So from this line I can write down 2RL into RTH plus RL will be equal to RTH plus RL whole square. Now see, we can cancel out 1 of RTH plus RL from the right side. So I can write down RTH plus RL will be equal to 2RL, from which I can write for maximum power transfer RL has to be equal to RTH. Let's say this is equation number 3. From equations 2 and 3 we can conclude that for maximum average power transfer the load impedance ZL must be selected so that the reactive part of ZL should be equal to minus XTH and resistive part of load impedance must be equal to RTH. That means for maximum power transfer theorem we can write down ZL is equal to RL plus J XL. For maximum power transfer RL has to be equal to RTH and XL has to be equal to minus XTH. Now see, in the circuit we represented ZTH by RTH plus JXTH. That means this RTH minus JXTH will represent the complex conjugate of ZTH. So for maximum power transfer theorem ZL has to be equal to the complex conjugate of the Thevenin impedance ZTH of the circuit. Now see, for maximum power transfer theorem XL is equal to minus XTH and RL is equal to RTH. See here, if I put the two conditions for maximum power transfer theorem in this equation, I will get VTH square over 4 RTH square. Here if I put XL equal to minus XTH, this term will be reduced to 0 into RTH over 2. So the maximum power will be equal to VTH square over 8 RTH. This is the equation of maximum average power that will be delivered to the load impedance. So for the circuit, the maximum average power will be equal to PL max, which will be equal to VTH square over 8 RTH. Here this RTH will represent the real part of the Thevenin impedance of the network. Okay, see, or complex conjugate of the Thevenin impedance of the network. That's it. Thank you.